now when I'll be writing something, okay? Okay, I apologize. It's too much of me, I understand, but I'm leaving tomorrow morning. There are no flights on Shabbat, so this is my last lecture. And I want to give you some good news. I already told you so much how everything is terrible, whatever we assume is wrong, whatever is supposed to be conserved is not conserved, whatever is supposed to be symmetric is not symmetric. And now a piece of good news for a change. And the end will be bad news again, but on a different scale. We'll do 2D now, and most of you know, so I'll just briefly recap it, that 2D is very much different from 3D, even in compressible flow, because it has extra conservation law. It also conserves vorticity and every its power. And you may say, okay, so what's the news? Because we also have Kelvin's theorem in any dimension, right? So this vorticity is kind of vorticity flux or velocity circulation conserves as we go, which means that you can kind of take a vortex, you can expand it, and it would shrink, or you can shrink, and the vorticity would expand. The point is that in arbitrary dimensionality, it's not a conservation law in the usual sense. It's a non-local quantity. The circulation of velocity assumes that whatever small, but there is a contour. There is no local density. Sometimes some people think that it's like angular momentum conservation. No, angular momentum has a local density. It's just V vector product with some R. But generally, Kelvin's theorem corresponds to a very non-trivial symmetry, which is a reliable symmetry of Lagrangian particle, and it does not have a local conserved density. But in 2D, vorticity is not a vector, it's a scalar, right? So I have a flow, and vorticity always looks up. So it's a pseudo-scalar, and it has a conservation law. And as a result, in particularly, not only V squared integral, but also curl V squared integral are conserved. Or if I write it in Fourier space, it means that I have a spectral density of Vk and k Vk, they both integral over all wave numbers is conserved. So now we immediately understand that if I have a two quadratic invariance, quadratic with respect to velocity, it means that I must have two cascades. And the argument is very simple, and it's a very simple algebra. So imagine that you would have a k space, and at some k1, you input v1 squared, that much energy, right? So then you have somewhere k3, and somewhere let me call it 2. So it will be k1, k2, k3. That's hierarchy. And so you expect that you would need to dissipate some v1 squared 2, and you need to dissipate some v1 squared 2. Now, because energy is conserved, you would immediately write that v2 squared is equal to v1 squared plus v3 squared. I'm extremely kind of simple-minded here, right? So this energy dissipate plus this energy equal. But also, on the other hand, I need to say that k2 squared, v2 squared, is k1 squared, v1 squared plus k3 squared, v3 squared, right? That's two linear equations. So we can easily solve it and express v1 and v3 in terms of v2. So if I say that v3 here is v2 squared minus v1 squared, right? And now I would put v2 over here, so it would be k2 squared minus k3 squared v2 squared equal to k1 squared minus k3 squared v1 squared. So I immediately obtain that v1 squared equal to v2 squared, and let me just, so it's k3 squared minus k2 squared divided by k3 squared minus k, here is 2, and here is 1. Okay? So this is how much energy I need to absorb right here in terms of how much energy I input. So now what I would do, I would keep this finite. I just send case 3 to infinity, right? So again, this cascade or whatever, this interval is finite. But you see that when case 3 goes to infinity, this goes to unity. Which means that all the energy is absorbed here, no matter the ratio of scale. It could be like 3 or 1.1 if case 3 goes to infinity. Okay? And that means inverse cascade. All the energy pumped here is absorbed here. Right? Which means that now for 2D, all the things that we did, something like, you remember, equal to minus 4 epsilon is also true. But for these formulas to make sense, we need epsilon to consider negative. Right? And which tells us that the same delta V cube longitudinal would be, you remember the general formula, d plus 2. Now d is, so it's, well, d it's 2 and d plus 2 is 4, right? Just, it would be a different factor here and a different sign. So, and this is something which was invented by Krykman, too, by the way, for which he got his Dirac medal with Zakharov, who obtained such an inverse cascade for waves on the water without understanding what he was my advisor when I was a student. And it tells us that we have another Kolmogorov-like turbulence, but this turbulence is somehow much, much better for original Kolmogorov idea. First of all, as I said, this is also ddt of delta V squared Lagrangian, which means that now in 2D, if I look at delta V squared as a function of time, it goes up and not down, and eventually it would also go up. Also, if you look at Richardson, you can look at Richardson from a very, very naive perspective. What it would do to have distance between two particles grow like T cube? What kind of a simple model you could have for it? Well, you could have a diffusion of velocities. Just imagine that ddt of R12 is delta V R12. So you have 2 points, and imagine that you have different forces, random forces, uncorrelating, acting on every velocity, right? Then you would have velocity squared growing linearly, and the distance would grow cubically. But it's more or less what we have in the inverse cascade, because in the inverse cascade, the pumping is at large K. It's a small scale forcing. I'm not saying that it is what is, because when I first realized it and I was a grad student, I was ecstatic. So I say, okay, let's make a model with a random forcing acting on every fluid particle. Then velocity difference would grow by diffusion law, and this would grow, and you can compute the factor, and it's not the factor that you measure. Of course, it's a nonlinear system, and it's a two-dimensional Navier-Stokes equation or Euler equation at large scales, and there is a pressure. But what I'm saying is that there is something which kind of does not contradict Kolmogorov scaling, because if you look at this quantity in 3D, let me remind you, the Kolmogorov relation, this one, imposes this evolution of delta V squared. So to get into this growth, you need a long, long time, and who knows what this type of growth would be. Here you're already on the right trajectory, namely the square difference between two fluid particles grow linearly as if they make a diffusion, right? So this is something which nobody, and we tried hard, maybe not hard enough, were able to put in any type of a rigorous argument. But it is this feeling that somehow all these troubles with this anomalous scaling and all this somehow should not be present here, all the more that our cascade now from small scales to large scales. One may say that why would you expect that you have a large scale forcing in 3D and it really imposes correlation on a scale of forcing. Now you look at small scales and somehow you expect to be independent on this scale. Why? You're still inside the correlation radius of it. Now you are in 2D in the inverse cascade, right? So when you look at this case, you look at scales which are much larger than your forcing scale. So you may say, I mean, look, I look at one particle and you look at another particle, and here is the correlation radius of my forcing. So there are different forcing acting on these points. And if I really average over my forcing, then there could be something which would be already independent. So it's more like a usual effective series in quantum field theory. I'm going towards larger and larger scales, and as I'm going towards larger and larger scale, I'm more and more averaging over the small scales where my pumping imposes situation. It's in any way represent any proof. I also believe that there is something geometrically very degenerate about 2D. In particularly, I think that one can probably prove something of Richardson type scaling just using the fact that you move in a plane. There is something must be about it which I will never able to pin, but kind of have this intuition. So all this kind of was lamentations, but experiments supported. Again, not that cleanly as we would want, but if one plots delta V in the power n, it scales like epsilon r in the power n over 3. There are kind of sometimes once approximately in 15, 20 years, some new numerics usually comes and say, yeah, we've seen some deviations here, some deviations there, but then eventually it kind of got sorted out. So we have a normal scaling. It does not mean that you don't have all these beauties related, for example, to passive scalar. If you put passive scalar in this scale invariant velocity field, as beautifully shown different people, and Antonio Celani, that you really would see an anomalous scaling of passive scalar inside it. But velocity itself seemed to be scale invariant. And at that point, when physicists see scale invariant, we naturally got greedy. We want more. What more you can want on top of scale invariance? I mean, scale invariance of the probability distribution delta VR. What's more you can want? What is of which scale invariance is a particular case? It's something called conformal invariance. And it's was suggested by Polyakov. Maybe the person who more than anybody established a bridge between a classical, well, Krajina and Polyakov in a sense, classical theoretical physics and field theory and turbulence. Polyakov suggested long, long ago for critical phenomena, you can take a physical system which exists at a finite temperature and it has a finite correlation radius, let's say, between spins. And then you kind of start to hit and hit and hit it, and you come to a Curie point, so that you're about to lose your magnetization. But at this critical point, you are at the verge of losing your order. So when you look at your system, you would see magnetic domains of all scales, right? it's something which very much reminds turbulence, where we have all this distribution of vortices of all scales. But the difference, of course, is that for systems that usually people consider in critical phenomena, they are local. Spins interact locally. There are exotic systems which are now studied more and more when you have kind of very long-range interaction, and in particular Coulomb system or system with gravity, they are long-range interaction. But mostly we're dealing with the nearest neighbor interaction. And in such situation, when you look at criticality, and that's what Polyakov suggested as a hypothesis in 1990s, and then it was spectacularly shown to be true for huge classes of critical phenomena, that statistics of fluctuation is not only scale invariant, but also conformally invariant. So let me explain what it is. Scale invariance essentially means as following. And you look at your domain, and then you expand this domain and also a little bit blur the resolution so that they would be in the same proportion. And you say, what will be statistics the same? In turbulence, in 3D, we already learned that it is not true. If you really blur enlarge the domain, you get closer to your pumping forcing scale L, and your statistics is not scale invariant. But if it is scale invariant, like in critical phenomena, and your interaction is local, then you get conformal invariance. What is conformal invariance? The most powerful thing, it is in 2D. It essentially tells you following. Imagine that you have some domain D, and some another domain D prime. I'm now pretending to be a mathematician, so I guess in front of Edris and Vlad, but they correct me if needed. So you have two domains, and so you naturally have a map from one domain to another. As Baryan similar, you can always map one domain into another. Now, do your critical phenomena. Put your Ising two-dimensional lattice of spins here, and then you put your lattice of spins here. And consider whatever statistics, for example, there could be some points Z1, Z2, Z3, whatever, and there could be some measure in the domain D of your points Z1, Zn. Okay? Now, under this map, these points map into some points over here. They come some kind of distorted or whatever. So you can also look here for the statistics on D prime of Z1, Zn primes. The statement is that the system is conformally invariant if those are the same statistics. So you can actually get all the statistics here just by computing, let's say, 3-point velocity correlation, or V1 minus V2 times V3, or omega here, whatever. So this is which essentially means that this function, which is an analytic function, it does the following thing. Analytic function generally is non-uniform. Namely, some domains here it expands, and some domain it contracts. What it does not do if it's analytic function, it does not change angles, right? Analytic means that your derivative is all direction is the same. So essentially, conformal transform, and it's very powerful in 2D because any function, it's infinite dimensional group of symmetry, if you wish. So essentially, it tells you that at some region, you may kind of contract things, but locally isotropically. In some other region, you can expand things. But you go from here to here smoothly and without distorting angles. Because your system is scale invariant and also local, so here locally you do not know that here you expand. Here you just kind of contract and your system is scale invariant. Here your system is also scale invariant. And you smoothly go from one to one. And this is a very powerful idea because in 2D, it's really an infinite dimensional group. And it immediately tells you a lot about your statistics. It imposes a lot of restriction. And it's usually that if you know something about your system, for example, you're doing Ising model, or you're doing Potts model, or you're doing percolation. In a moment we'll come to percolation. I explain what it is. Then you can just measure a couple of exponents, and you know all the other exponents, all the other critical indices, all the other correlation functions. They are all determined by some representation of conformal group. So this is as close as we can to the classification of universality classes of critical phenomena. And so far it exists only in 2D. And we don't have much generalization for higher dimension. Okay? So the moment that we've seen scale invariance in two-dimensional turbulence, of course it's non-local, right? Because there is a pressure. And pressure is determined by inverse Laplacian of velocity, which is as non-local as one gets. But we can kind of dream, and so we started dreaming, and Polyakov was first in 1993 to suggest to look for conformal invariance in turbulence. And I remember that was kind of silence. So Polyakov published this paper, and turbulence community kind of did not respond. I remember, like everyone. And then I was asking people, and I was very young at the time. And so eventually I kind of responded saying that no, it could not be. It just, it contradicts kind of irreversibility, several things. And some 15 years later, I, with Guido Buffetta, Antonio Celani, and Denis Bernard, proved myself wrong. So we found conformal invariance. And this is what I'm going to tell you. Something truly strange that we found in two-dimensional turbulence. But for this, I want to introduce a really mathematical idea which is different from what we had before, namely all these PDE, ODE ideas of dynamical chaos, PDE ideas of weak solution. This is a little bit different mathematics, and the beginning of it is called Löwner evolution. This is something which I remember when I first learned it, and one great person who recently died, Krzysztof Gawecki, told me, you need to learn this. And I was in such an awe of him that I went and learned this new mathematics, even though I didn't know why I needed it. So Löwner evolution is the following thing. It's a way to map any curve into motion of a point on a straight line. So let me explain what it is. Imagine that you have a half plane, and you have a curve growing from the boundary. Okay? Let's call this curve gamma, and it's a function of time. The time is just coordinate along this curve. So now what I can do, I can map the domain, which is a half plane without this curve, into just half plane. Assume that this is a slit, right? So it's also part of the boundary. This is a part of this boundary, this is this, and I can map it like absorbing it into a boundary, right? So this would be some function, g, which would be a function of z, and would be function of t in the sense that as I would continue this curve, this map would change. And as usual, it maps boundary into the boundary, so the tip of this curve would map into something which, let me call zeta of t. Okay? Now, as my curve goes, this changes and this moves, but it always moves on the boundary, right? It's called a Löwner evolution. It was Karl Löwner, and then he changed into Charles Löwner when he ran out of Germany at 30s. Then one can ask what is the equation that is satisfied by this map. And surprisingly, and this is the most beautiful part of this Löwner evolution, is this equation is completely determined by this point. So first of all, you say that it's a finite curve, so this g, when you consider limit of z going to infinity, it just must be z. It's identity, right? So very far from my curve, this is just this maps to this. And then you may say that what defines this is just an expansion. And so you can say that there would be something. And this is, in a sense, give you kind of a normalization. This is some kind of a definition of this parameter theta. And then you, what Loevner defined is this equation. Okay? So, which means that you know this, you solve this equation, you get G. And this is something which is a very, very it's kind of an ordinary differential equation, and it tells you that you can encode however complicated shape into the law of motion of a point on a straight line, and mathematicians is kind of used it in a very, very creative and different ways. It's 100 years already in use. And then 80 years later, an Israeli mathematician Schramm, so it's now called Schramm-Loevner evolution, asked a very natural question. What happens if this is a random walk? Okay. So, I mean, you can solve this equation and see what kind of curves correspond to different. But so if you now move this by a Brownian walk, that the only thing that you need to define is essentially this kappa. It's now a dimension. Everything is dimensionless now, right? So this kappa is the only things which tells you how kind of curvy your curve, right? As kappa going to 0, it's practically standing at place, and so you just have a straight line, and then if you a little bit wiggling, etc. So in a sense, this kappa is what determines this. And the most interesting thing which was proved, and again, it took, I don't know, maybe Vlad knows exactly, at least two Fields medal, and Adet himself did not get it because he was already 41 when people understood how great he thinks, and then he unfortunately died in a mounting accident. But people proved that if this is a Brownian walk, then the statistics of this curve is conformally invariant. Exactly in a sense which I've shown before, that you can compute any probabilities. At this point, it was still mathematics. And at this point, physicists started to warm up to it because physicists in critical phenomena used to work a lot with lines. For example, in Ising model, you have boundaries of domains. You have spins up, and there is a boundary, and outside this boundary spins are down. Okay? And then you ask what kind of a statistic. Those are random curves, and it happened to be exactly corresponding to SLE of kappa equal to 3. But there was even simpler case, which is called percolation. And percolation is sometimes mentioned as the simplest critical phenomena. You know what is percolation? Somebody heard about it? Okay, good. So let me remind the rest. So imagine that you have a landscape, kind of mountains and valleys like around us. Okay, it's a which means that it's a function h as a function of x and y. So it's a height as a function on a plane, like kind of mountains, etc. And you start filling it with water, right? So initially, when water is low, there is just series of lakes and ponds. As you fill it higher and higher, and this is, imagine this kind of a random function. As you fill higher and higher, at some point, these lakes started to be connected by channels, right? And then you ask, is there a critical point, namely critical level of water, in which there is equal probability to walk from one end to another on Earth or to sail on the water. And it's called a critical. And then you start looking at the boundary of your lakes, channels, and rivers, and it's a random curve. And you ask, what is this random curve correspond to? And you find out that it's kappa equal to 6. Instead, I'm not going into much details, what are the restrictions, etc. So what we found, to a huge surprise, is that if you look at a two-dimensional turbulence in this interval of the inverse cascade, and you look more or less at the same thing, but this would be your omega. Well, it's pseudoscalar. Imagine that you take just it. So it's you assume that it's turbulence. So on average, omega is 0. So there is as much positive omega as negative omega. I'm not using presentation, PowerPoint, etc. So I really advise you to look at this. This is a paper, Bernard, Buffetta, Celani, and myself in Nature Physics, where you can see, as really massive computation, how fractal is the nature of all these things. So we're interested in the boundary between cyclones and anticyclones, which corresponds to omega 0. Why I'm saying cyclones and anticyclones? This geophysical terminology. If you look at the atmosphere, it's a relatively thin 10-kilometer layer of a fluid on a scale of 6,000 kilometers. And a vortices which has one direction is called cyclones, and which rotates opposite to the Earth's rotation is called anticyclones. And we are very much interested in the statistics of lines between them. Why? Why meteorology are so much interested in this boundary between cyclones and anticyclones? That's where weather change. That's where it rains, right? So where is, you know what is anticyclone? Anticyclone means that you rotate opposite, and when you look from above, so you rotate opposite, and so Coriolis force acts in this direction, and your atmosphere is higher here. You create a local height of the atmosphere, so there is higher pressure. It's sunny, it's nice, it's beautiful. When you rotate opposite direction, your Coriolis force acts in opposite direction, and you create depression. That's where pressure is low, and it starts raining and all this. So it's a very, very natural object. And what we found out is that this line exactly corresponds to Schreiber-Loebner revolution. It's a fractal line. It has a fractal dimensionality 7/4, which means that it's not a simple line. It means that it has something like a double point. It returns to itself, and it can also go in and then return out. So you can look at its envelope, and it corresponds to a simple line. You don't go in, you just go outside it. It's called hull. So something which is visible from infinity, and it has dimensionality 4/3, and it's actually how it's all started, because Gavetski forced me to learn this SLA, which I did not know what for. And then at some point, we were sitting with Bernard, who is a quantum field theory person, Denis Bernard from Paris, and he was telling me that a different dimensionalities of different conformally invariant curves. And I say, yeah, well, I know 4/3 because I think that the zero vorticity line has this dimensionality. I had some argument which was completely wrong. Like argument of Carnot of the growth of entropy was totally wrong, but the statement was correct. So I had this prediction for all the wrong reasons, and then we asked Celani and Buffetta checked it, and they checked it was 4/3, and then they checked that it's 7/4 if you also include inside, and then we started to check whether it's really conformally invariant. And this is something which I really want you to tell, because this is something which is a simple test, and there is online library which you can always use. You just take a program, and whatever line you have in your numerics, the point is that you take this zero vorticity line, just arbitrarily make some half plane, and then start kind of absorbing it. In a sense, you start building this function numerically. So you break it, and there is a standard algorithm which you can just take, download, and check. And after that, people did it for surface quasi-geostrophic model, for Hasegawa-Mima model. There are many, many two-dimensional turbulences with inverse or sometimes direct cascade, which satisfy this relation. And so as you absorb it, you build this function, and at every time step, you get this function as a function of time. So the net result of this numerical procedure would be zeta of t1, zeta of t2. This is your time step, zeta of t3. And then you just check that this Brownian motion. Just independent of it, which is a very, very, again, online powerful algorithm. The moment that you identify whatever curve you have, and after that people did it to coastal lines. You know that the coastal lines is the first kind of example of a fractal. But there are two types of coastal lines. One is kind of sandy and another are rocky. So rocky coastlines are SLE, sandy coastlines aren't SLE, and nobody knows why. And of course, nobody knows why zero vorticity line belongs to the same universality class as percolation. Yes? Well, in a sense, you get a lot of statistics just from a single snapshot. Guido and Antonio did numerics. Back then it was kind of, it was like 10,000 squared. So you get a snapshot of your vorticity field, which consists like, I don't know, 200 different clusters already, or like 500 different clusters. Oh no, we have forcing. No, this was a steady turbulence. It took 2 months. One run takes 2 months on supercomputer, right? So you just switch on forcing at small scales, which is approximately 300, a ratio of your box size to the forcing scale. And you run this 2 months, and then you get stationary statistics. Then you take snapshots. You, at this particular case, we had, I think it's hyperviscosity at small k, just to stabilize these things. But you work in a really good interval between your forcing scale and your domain scale, and there is no time. You just take a snapshot and you ask. I mean, and it's really it's unbelievably fractal, right? And then you just go along it and do what we call Schramm test. Namely, you just check that if you map this line into a Löwner evolution on a straight line, it would be a Brownian walk, and then you measure kappa. And you get kappa 6 with accuracy of like 5% and then 3%, which is not a proof in any way. But it's a really very strong indication. And then we did it for surface quasi-geostrophic, and then Antonio Musacchio did it for the whole classes of geophysical fluid mechanical models. Nobody has any idea where it follows from. Where in the Euler equation or surface quasi-geostrophic equation it's encoded. Question? What D? This is D over 8 plus 1, I guess. This is 16 over D. There is a formula which relates this D to kappa over 8, and this is 16 over kappa. So by kappa, you immediately read your dimension. And these two dimensions are related. There's some kind of a duality between a curve equation. It's related to phase transition in a sense that phase transition taught us the idea of conformal invariance. In a sense that if you have fluctuations of all scales, And then you assume that it's scale invariant in the sense that if you have a fluctuation of all scales from domain size all the way to atomic scale, then at whatever part of the picture you look like, this large, or that large, or that large, will be more or less look the same. If on top of this you say, okay, but it's also local, namely that here it does not depend on what is there, then you can ask if it's invariant not only with respect to uniform rescaling, but with respect to non-uniform rescaling, which it does by conformal transform. So you do it conformal transform, so here you contract, but here you expand, but you smoothly go from here to here, and you preserve angles. And what Polyakov taught us, and since then we learn it's true, that in phase transition and critical phenomena in 2D, local field series are conformally invariant. No. 2D turbulence is not conformally invariant. A small part of it, this one. And then here good news end, namely that when you say, okay, but what about omega as a field? The answer is no. So the spin field for or phi, if you wish, it continuous limit for Ising model is a whole thing described by conformal field theory. Turbulence is not. We have only one indication of it, which, by the way, was never published, and Guido Buffetta computed it. And so Zamolodchikov, Buffetta, and me, we did it. We have shown numerically that a 3-point correlation function of omegas in this inverse cascade of two-dimensional turbulence is non-zero. Without going into details, it tells you that it could not be a conformal field theory. Conformal field theory cannot have triple correlation of a pseudoscalar, and I don't want to go into all these details. So the net result is as following. Turbulence as a whole field. You can say that omega as a field is whole turbulence, right? You can read velocity by Bio-Savart from here. It's not conformally invariant. If you transfer your domain by conformal transform, then the statistics of omegas are not invariant. But the line omega equal to 0 is conformally invariant. You see? Which means that this line is very insensitive what you do with the rest of the field. Like, you can just take omegas enlarge, just omega 0 is something that whatever factor you multiply is still omega 0. Sometimes I think that it's what remains from potential flow. So if you consider a domain where omega equal to 0, it means that it's a potential flow. Potential flow of incompressible fluid is literally conformally invariant because the velocity is determined by a complex potential. Right? It's div v is 0 and curl v is 0. Those are Cauchy-Riemann condition on a stream function and potential. So in this sense, sometimes I think that this, what remained, so if you now shrink the domain omega equal to 0 into a line, but you always have lines omega equal to 0, right? Having a domain of omega equal to 0 is very, very degenerate, but lines you always have. So this is something which I wanted you to tell because I spent a lot of time, like 3 years, and then it was wasted 3 years, was trying to understand where it comes from. Where this kappa? Why for surface quasi-geostrophic kappa equal to 4 and for Euler kappa equal to 6? What the hell? Where it's written? Yes.
So you said that for like different types of coast you have different kappas?
Yes.
So when you have like, for example, a turbulent wake or a turbulent jet in the laminar inflow and you take a picture, then you also have like a fractal interface of turbulent, non-turbulent.
Yeah, this all 2D. So if you have a wake in 2D, in a sense that you really have a thin layer, you move disk and you have a wake, then this is something which is related. In 3D, there is no analog. In 3D, nobody can work with surfaces, and in 3D, conformal group is finite dimensional. This all is 2D science. Okay. More questions? Oh yeah, It's very non-local.
So, I mean, what did you I mean, it breaks one of the other two.
What I can guarantee that incompressible fluid is very, very non-local. You hit it here, it feels there. That what incompressible means infinite speed of sound, for God's sake. So the pressure exactly, you remember we always write this relation which is give V grad V equal to Laplace pressure. So your pressure is Laplace minus one of this. It's a very, very non-local object. What I can guarantee is that dynamically incompressible fluid is very, very non-local. I don't even want to go there. could be conformal invariant in a different way. Okay. Any more questions? Yeah. Point vortices are already singular object, and this is something which is about fractal but continuous curves, right? I had this dream that I may try, because we know that if I take point vortices, which is a kind of Coulomb gas, right? They are like charges. Only charges interact like this, and vortices do to each other a transversal force. We know that if you have a set of point vortices in equilibrium, their statistics is described by conformal field theory. It's conformally invariant, right? The moment you impose non-equilibrium, you lose everything. Again, in these 3 years where I was fighting with this problem, I tried to use a point vortex model, and Zamolodchikov always told me that you'll fail. It only works at equilibrium. The moment you deviate your point, your Coulomb gas from equilibrium, everything. And he was right. I mean, nothing came out of it. KPZ is not a turbulence. It's again something which is driven by a white noise. There is no flux in KPZ. It has a non-trivial scale, etc., but it's still it's not the same thing. Question?
Does it make sense to do the fractal circulation
Huh?
to apply Turbulence circulation to the conformal mathematical transformation?
Yeah, well, in a sense, in this two-dimensional turbulence, there are many things which are related to, in particular, you may consider statistics of vorticity fluxes through different regions, or which would be a velocity circulation, and then you may ask for different statistics. This is not about this. This is only about the boundary between cyclones and anticyclones. Okay, so it's in a sense, as this field theory people say, a slice of statistics or sector of statistics is conformally invariant, but not the whole statistic. Yes, Idris?
Point vortices, just a remark, I don't know if it's relevant or not. Usually it is known that point vortices take a base of equation, which is like all Karaman kind of like system ODEs, but they don't really satisfy Euler equation itself. It's inspired by, but not exactly, they're not solutions of Euler elements. Although there are some models, which is like the Euler alpha, in which point vortices are solution of the PDE. Do you think this has anything to do or not? Because one is solving an ODE in which the velocity field is not really only the point where they're moving, but it reduces vector field, velocity field around by the velocity.
Dynamically, you can, it seems, and again, I'm not a mathematician, that you can consider appropriate limits at which this motion of a point vortex, an appropriate limit of n going to infinity, reproduce dynamically the flow. But when you try, and I did, and my students did, and every time we failed, to reproduce an inverse cascade using point vortices, namely, what is inverse cascade? Is a clustering of vorticity of the same side, right? So essentially, what you expect, you start from positive and negative vortices randomly distributed. Then you do something. Eric Sijer was first who did it, and he did it beautifully with Arif in 1980 something. it was first Cray, so they had like, I don't know, 50 vortices, and they started to see 5/3. And then everybody said, okay, Eric knows how to West-point vortices. Then 20 years later, a student of mine, Maria Vutsila, I don't know, you probably know Maria, this is big, she's now a professor, but back then she was a student with mine. She just reproduced Eric result, and then, because it was already not a simple supercomputer, but a big one, made it like 100 times more resolution, and everything disappeared. And after that, we tried many, many times, and we never, Guido Buffetta and Antonio Cialani spent a lot of time trying to reproduce inverse cascade using point vortices. We never succeeded. So I don't know, maybe it's possible, but I don't know how to do it. And for me, point vortices eventually was not a good kind of way to model this. Even though it's very beautiful, it's just ordinary differential equation, right?
We'll talk about it later because X makes a difference because point vortices they obey system easy, which as you say is the Coulomb interaction with the logarithmic kernel. They don't obey Euler equation itself as a PDE.
Absolutely, yeah.
While for the Euler alpha they do. But that's different.
Maybe there is another model for which you can do. Okay, now I want to end this. I have 10 minutes. And I want to, as promised, to finish with bad news, but I want to return to the very, very first subject for which I started my first lecture. I want to make a loop, okay? And this is about this flow. You remember? And at some point, I told you that I have this force G alpha acting in this direction, and instead of just saying that this is, we actually need to put here something else. And I say, okay, just let's forget this, and instead of this, we just put here a nonlinear term, and it would give us velocity, which would be v squared G alpha, well, v as at the height h, okay, v squared. Let's call it, and it seems now as if we have the same situation as in a flow with separation, what Prandtl did. Wait, it does not erase. You remember that when we were looking at a flow with this, and when we're asking what is the force acting divided by rho u squared r squared, we get it eventually coming to a constant. So it could seem like for this flow, it would be also like this. This is your force. This is kind of your velocity. What I now want you to tell in the remaining, I don't know, possible 6 minutes, the same situation with the pipe. If you just replace this with grad pi over rho, and you say that this profile like this, imagine that there is a pipe. That would be a pipe flow. And what we know for pipe flow, that this is not true. Okay? And the reason for it is that when we were doing this, we were kind of assuming that this turbulence which is inside and which transports the momentum to the bottom and provides for a final thing, it's kind of homogeneous. Well, it's not. It's dependent on z. This is a z coordinate, right? So essentially what you can realize is that this profile of velocity must have a logarithmic form. So what you really have here, if you just write equation of motion, that you have here d dz of nu du dz. This u is in this direction. It has also u in this direction, and it also has v in that direction. So what I'm now doing, I'm assuming that I have a mean flow, and it has also fluctuating components u and v. And this is the main problem of turbulence. Namely, real turbulence is never isotropic homogeneous turbulence. It's always turbulence inside the flow. And the real problem, Nobel scale problem of turbulence is actually how the flow interacts with turbulence and what kind of a flow determined by turbulence and what kind of turbulence is determined by flow. So you can just by simple manipulation show that this what stands here is what is called a Reynolds stress tensor. Okay. So now you can say that this is let's call it sigma. This is our this is our flux, and then you immediately recognize that this sigma, which is a momentum flux, is just sigma of 0 minus alpha g z, and because this is sigma of z, and because you assume that sigma of h here at the center of your pipe or on the surface of your river is 0, then you immediately recognize that sigma of 0 is alpha g h, and we also would call it v squared according to this notation. And now I want to give you a very simple argument which shows how different is this situation from this situation. And this is an argument about the mean velocity. So you say that if you have a mean velocity and you make, it's a function of z, right? And you dimensionalize it by the only parameter having dimensionality of velocity. This is your parameters, g alpha h. Oh, this is grad p over rho if you are in a pipe, right? So this is a dimensionless number, and it must be function of a dimensionless numbers which are what? What are dimensionless number in these problems? We have z and we have h, right? So let's make dimensional number out of it. Let's call it L. And then we also have viscosity. And out of viscosity, we always do what? We do Reynolds number. And the Reynolds number we can do like this. Okay? So this is some function of these two dimensionless variables. And now, a noble scale problem, even without describing all the correlation function of turbulence, is to get this function, right? And we cannot, but we can argue in the following way. We can consider different limits, right? So we have this z, which runs up. Here is z, which runs up. And we may say that when we consider z much less than h, right? Then we expect that this is the real, and this is L. Okay, this is my notation. This is the Reynolds number, and this is L. Okay, so when z is much less than h, then I expect that my h disappears, right? Which means that my u at such z divided by v star must be some function of L times real. Because you need to multiply this by this so that h would disappear. Okay? Then you may say, but when I am here near the center, what I really expect that what is called deficit, if I take u of h right here, that where is my maximal velocity, and may subtract u of z, and again divided by v star, I expect it to be function only of L. Because now I am very far from the only region where my viscosity can play, right? This is my boundary layer where viscosity play. So I expect Reynolds to disappear. But of course, this quantity u of h over v star is something which is only a function of real. Right? This is just a kind of a mean velocity through my pipe, and it's only function, it's a dimensionless number. It does not depend on z in any way. It's already taken at a given z. So this is some f2 of real. And then, as I already have no time, I'm giving a last kind of hit. I'm saying that I assume that there is overlap. That this and this somehow have a region where they overlap. And then I would get that this is equal to this minus f2 F2 minus F1 of L. What we immediately recognize that this all three function must be what? Logarithmic. Okay? Immediately, if this assumption is true, and if you prove it, you can get Fields Medal, and if you derive it, you can get Nobel Prize, depending on which department you work in. But it immediately tells you the following thing, that if you now consider this u of z is v star, and it's a logarithm of v star h over nu. So when nu goes to 0, this goes to infinity. It's a slow law, but it goes to infinity. And the friction factor, of course, it's v divided by u squared, and it's 1 over log square of your Reynolds number. This is all assuming that you have infinitely smooth bottom. You see? And that's why I really want to end with this. I want to show you how different physics are here and here. Of course, if here you would have some irregularities at the bottom, any irregularity would produce wake and be like here. So this logarithm would stop, determined by the non-smoothness of your boundary. But why I'm showing you this two picture? Because I think, and I started to think recently relatively like this, the turbulence community did not before, it now more and more, appreciate how different turbulences are inside. I don't think it's the same turbulence there and there. In the pipe and in the wake, I think the turbulences are very, very different. In particular, in smooth pipe, it does not have dissipative anomaly. Okay? And it's for your generation to sort it out because we failed. Let me finish at this point. I don't know if we allowed questions or we just can do it in form. Berenger, what we can, it's already. Okay, good, because I already stalled 3 minutes. I apologize, but questions?
Actually, regarding your last statement, when people talk about experiments, real world like lab experiments in which they see dissipation anomaly, where do they perform in the pipe or where?
In a pipe, they see that if they polish pipe more and more, dissipation is less and less. Resistance is less and less.
So in other words, you're saying, you claim is that in pipe, there shouldn't be dissipation anomaly.
In infinitely smooth pipe would be no resistance.
Is there any other evidence of dissipation anomaly other than experiment in the pipe?
What do you mean? Dissipation anomaly or wake? You have wake. You can just, you shoot bullets and you measure resistance. You know.
Model of zero law, people based on experimental data, where this experiment have been performed.
For what?
Apparatus.
For what? What experiment? For what? I didn't understand your question. What what proved? What statement?
In which it's observed that the new rate of dissipation as viscosity getting smaller and smaller tend to a constant.
Wake. Any wake does this. Karman flow, what Berenger told you. Anything which is not straight lines demonstrate dissipative anomaly, as far as we know. Or non-smooth pipe. Yeah, absolutely. Just make your pipe kind of, like smoking pipe. Okay? And that's it. You don't have straight lines. So this is, here we're pretty safe. There's a lot of data up to Reynolds number so that we already come into supersonic flows. Yeah. Somebody? Yes. Of what? Good question. Good question. We did torus. We are numerical people, which means that in this case, yeah, which means that we did torus, and it could. Nobody did it on a sphere. Just Go did it on a sphere. It's curved surface. It's a nightmare. But it's really interesting on a sphere because that's where we live, right? Yeah. More questions? Yes. Yeah, up to some age, when I was young, I believed that at every even dimension we will have inverse cascade, and then at every odd dimension we don't. Because at even dimension we have analogs of vorticity. Of course, now this vorticity, it will be some kind of antisymmetric matrix, but then Toshi Goto shown me that at higher dimension, all these invariants related to vorticity not sign definite. And he directly proved that in 4, 5, and 6 dimensions there are only direct cascade. Okay? And it changes with dimension very interestingly. But that's different story. Yes?
So you said about your last statement that the turbulence in the wake is different from the turbulence in, let's say, a smooth pipe because they are, for example, straight lines. But what if you have like a curved pipe?
If you have a curved pipe, I think that it could be different to a less extent. I think this is something which is not really explored. As much data that I've seen, and you'll have some lectures about this, turbulence in a pipe in no way is Kolmogorov turbulence, right? Even at a scale which are much larger than the scale of your roughness of the wall, okay? Because it's really important that you have a profile of the flow. This turbulence, I wanted to tell, but I did not have time, but in 2D, in the inverse cascade, you have inverse cascade and it creates eventually a big vortex. So again, you have a problem of turbulence interacting with the mean flow. And I solved this problem. In 2D, you can solve it because your turbulence is kind of simple and trivial. How to do it in 3D? It's to get logarithmic profile.
So follow-up question. So is it right that you say that when the pipe is then getting from smooth to rough, then the turbulence is changing from non-Kolmogorov to Kolmogorov?
No, I didn't say it. It just acquires dissipative anomaly. It gets finite resistance, which stop depending on Reynolds number. So it stopped dropping, right? But it's still inside different because it's inside inhomogeneous profile of a flow which changes this turbulence. This turbulence not only provides for a spectral flux to small scales, but it provides for special flux of momentum to the wall. It's anisotropic turbulence and it's different. That's what I wanted to stress. They are very different. And it's not sorted out. Wait a second, yes.
So that means if we take a flat plate and the surface of an airfoil, let's take an example.
Yeah.
I have a flat plate
Yeah.
and the surface of an airfoil.
Yeah.
So the turbulence on would be different.
I believe that any wall-bounded turbulence at some distance of the wall is very different from, let's say, four-Kalmar flow where you try to arrange it. But when it's a foil, it's already, I mean, again, foil is something which has a wake which is very thin, right? So what is outside of the wake is more like pipe turbulence. But again, I don't know. It's really, I mean, my knowledge.
I have a motivation, like for example, one wants to show that these two turbulences are different. Which direction one should head towards?
Correlation function, just velocity correlation function. But with all full vector glory, not just a spectrum of energy, right? V1, V2, V3, here, here, here. Okay?
It seems to observe in the limit of having a perfectly smooth boundary and in the limit of zero viscosity, we seem to observe no anticipation anomaly in pipe flow. But what if we fix, no matter how small it is, a constant, let's say, roughness,
Yes.
and we limit dissipation, limit the viscosity to zero? Can we observe some anomaly?
If you fix roughness and you turn velocity to zero, that's precisely what Nikoradze observed. You get at your roughness Vx, and you would have your resistance you drag through your pipe independent on Reynolds number and finite. And this finite value depends on the size of your roughness. Yes? No, no, the fractal dimension would not change, but what you can compute any statistics in this domain by the statistics in this domain. Essentially, what conformal invariance gives you? You can always map from whatever idiotic domain you live into some kind of a standard domain, there compute everything, and then recompute it there. But also you get a lot of formulas for free. There are different Cardi formulas, for example, for what is the probability that this line enters a rectangle and it would exit through long side or not through the short side. There are some explicit formulas. So you can predict how your boundary between, cyclone and anticyclone, how it behaves, You observe part of it, you can predict statistics of how it would go from here. It's a lot of information. Oh yeah, you can expand it, you can contract it. Yeah. Oh, a total circulation is zero because your mean vorticity is zero. Yeah. This is not conformally invariant. There's only zero vorticity lines are conformally invariant. Yeah. I don't know this origin. Okay, if there is no further question, I just want to say that this is a prize. And today there were no questions and answers comparable with you, so that will go with you. And I would be happy to sign with it. So, Leyin from Lille, a local, yeah. So, congratulations. Okay, that's it. We ended. Thanks for all of you to surviving this. Okay, want me to sign? Okay. Yeah, thanks. So I just sign with you. Lei is